Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to model uncertain continuous quantities using continuous random variables. This is going to be an overview, so don't worry if you don't understand some of the details, they will be explained in the following videos. Let's get to it. We're going to give an overview of continuous random variables. Our motivation is that there are many quantities that are more naturally interpreted as being continuous as opposed to discrete. For example, length, mass, time, and in fact, most physical quantities. Our goal is to define continuous random variables so that we can model these quantities when they are uncertain within a probabilistic model. I said model. Notation is the same as when we talked about discrete random variables. When we talk about deterministic variables that have a fixed value, even if it's unknown, we write them without a tilde, without a squiggly line on top. But every time you see a squiggly line on top, that means that we have an uncertain quantity, which we model as a continuous random variable. So what is a random variable? Well, it depends whom you ask. If you ask a data scientist, they will answer, well, it's just an uncertain variable that is described by probabilities that I can estimate from data and which I put into my probabilistic models. Okay, and that's very reasonable. However, if you ask a mathematician, they will give you a very different answer. They will say it's a function mapping outcomes from a probability space, in particular from a sample space in a probability space, to the real numbers. So now we're going to try to connect these two perspectives, the more practical perspective of the data scientist and the more mathematical perspective of the mathematician. So what is the plan? First, we're going to go over the mathematical definition of continuous random variables, and we're going to see that it makes some sense, even if it might seem intimidating at first. Then we're going to talk about the cumulative distribution function, which enables us to describe continuous random variables using their probabilities. Then we're going to talk about the probability density, which gives us another description of probabilities associated to a continuous random variable. And finally, so just to be clear, this falls within probability theory. We're going to be introducing concepts and tools from probability theory to be able to manipulate continuous random variables in a mathematically sound way. But then we're going to switch gears and we're going to ask ourselves, sure, but what do we do with data? And what we do with data is we model using continuous random variables. That enters the realm of statistics. We're going to discuss non-parametric modeling and parametric modeling. Okay? So this first part would be more probability. The second part is going to be more statistics. All right, so let's remind ourselves how we defined discrete random variables mathematically. If you don't remember, you can go back to the video, but the idea was that we had a sample space here, which is within a probability space, which means that there's not only the sample space, there's also the collection and the probability measure. And we defined the discrete random variable as a function that mapped points within this probability space, within this sample space, to 3 discrete points in this case, or in general to a discrete set. So here there's A1, A2, A3. All of the points here point towards A1 through this random variable A. All of the points here map to A3. And these guys map to A2. All right, and then we didn't obviously describe discrete random variables in practice like this. What we did is we said, well, okay, sure, they're defined mathematically like that, but we just need to know what's the probability that the random variable is equal to each of these 3 possible values in this case, or however many values are in this range, which is the set of possible values. And we just need to keep track of those probabilities. The probability in this case that the discrete random variable is equal to A1, A2, and A3. And that's what the probability mass function gives us. Okay, that was like a half-a-minute summary of how we define discrete random variables. Okay, perfect. So can we do the same thing for continuous random variables? Can we just say, sure, there's this sample space that is mapping to the real numbers, but what I'm going to do is I'm going to just describe the random variable using the probability that it's equal to each possible point on the real line. Can we do that? No, we cannot do that. We cannot do that. The reason is that, well, there's two reasons for this. The intuitive reason is that we're modeling continuous quantities. So think about it this way. What is the length of a single point on a line? The length is 0. What is the mass of a single point within an object? It's 0. What is the area of a single point on a map or on some 2D surface? It's 0, right? So if we're modeling continuous quantities, the probability of a single point intuitively should be 0. Mathematically, if you try to assign probabilities on the real line, because there are uncountably many points, the probability is going to explode. You're not going to be able to assign non-zero probability to each of the points and then make them all add up to 1 so that it's a valid, so that the probability measure is actually valid. Okay, so no, we cannot do this. So what do we do? Instead, we're going to describe continuous and uncertain continuous quantities, continuous random variables, in terms of the probability that they belong to different intervals. That's what we're going to do. So if we go back to this picture where we were looking at the random variable as a function that maps from a sample space to the real line, now what we need is for the probability that the random variable ends up here to be well defined. And that's exactly how we define random variables. We say that there's continuous random variables. We say that there's an underlying sample space within a probability space where each set of points that map to an interval, for example, these guys map in there and these guys map in there, again, through the random variable, let's call it A. Those sets of points that map to intervals all need to be assigned a probability measure in this underlying probability space. Of course, just like in the case of discrete random variables, we're never going to talk about this probability space except in the definition. As we will see, we'll just define some quantities that tell us the probability of the random variable landing in each interval. But this is the mathematical definition. The mathematical definition is there is a probability space, and in order for the random variable to be well defined, it has to be a function from the sample space of the probability space to the reals, such that, I feel that I drew too many things here, such that these events, these sets of outcomes that map to each possible interval are all assigned a probability. Okay? So here I'm just showing you a few outcomes, omega 1, omega 2, omega 3. Omega 1 is mapped by A into the first interval. Omega 2 and omega 3, because they belong to this other event, get mapped to the second interval. Okay, the important thing is that these events here must be assigned a probability by the probability measure of the probability space. That sounds really complicated. Okay, this is the mathematical definition of continuous random variable. It's a function, a continuous random variable is a function from a sample space to the reals, and we need for all of these events that map to each possible interval on the real line to be within that collection, so that they are assigned a probability, and we can talk about the probability that the random variable belongs to any possible interval on the real line. That sounds very, very complicated. And by the way, we actually, in this previous definition, could potentially include points that have non-zero probability, but when we talk about continuous random variables, we assume that each point is going to have zero probability. But you can define other random variables that do have non-zero probability in some points, in a countable number of points, and still satisfy the previous definition. Okay, so the problem here is that now we have the probabilities in terms of the sample space, but we don't want to deal with the sample space. We don't want to deal with the probability space. Just like when we talk about discrete random variables, we at some point forgot the underlying probability space and just dealt with the probability mass function. Well, here it turns out that we can do something very similar. Consider the probability that the random variable is either in one interval or in the other. It turns out that in order to compute that probability, we don't need to go to the underlying sample space. Why? because we can just add up the probability that A is in one of the intervals plus the probability that A is in the other interval. Why can we do that? So there is a mathematical reason for that, which does use the underlying probability space, which is that if you consider all the points that map to one of the intervals and all the points that map to the other interval, if these guys are disjoint, then these guys are also disjoint. But if these two events are disjoint, now we can reason within the probability space, and we know that the probability measure of the union, the probability of the union of two disjoint events is equal to the sum of their probabilities. This immediately implies that the sum of the union of the events that the random variable belongs. Oh, I got very confused there. Let me do that again. The probability that the random variable belongs to the union of two disjoint intervals is equal to the sum of the individual probabilities. Okay, we'll go, we'll provide a more complete justification for this in the video on the mathematical definition of continuous random variables. But the point is that we can essentially forget about this and just reason here. If you want to know the probability that a continuous random variable belongs to any union of intervals, you can reason with the probability that belongs to the individual intervals. And that's what saves us. This is what allows us to only reason with probabilities that are in this right part of the picture, which are more intuitive and much easier to deal with. Okay, so in general, if we have n disjoint intervals of the real line, the probability that a random variable belongs to the union of those intervals can be expressed as just the sum that it belongs to any of the intervals. So what I'm getting at is that in order to manipulate a continuous random variable, we just need to keep track of the probability that belongs to any interval on the real line. We don't need to keep track of the underlying probability space, and in fact, usually we will never even define it explicitly, that underlying probability space. It's just there as a mathematical abstraction to make sure that everything is mathematically sound. Hopefully that makes sense. So the conclusion is that we actually describe continuous random variables in terms of the probability that they belong to any interval. And this connects to the perspective of the data scientist, which was saying, well, at the end of the day, a continuous random variable is just a continuous quantity that I describe with some probabilities. Okay, and this is well justified also from the mathematical point of view. The thing is that now you might be wondering, okay, sure, but there are many intervals. How do I keep track of the probability that the random variable belongs to any interval? That seems a bit complicated. Well, there's two main ways of keeping track of this information. They are the cumulative distribution function and the probability distribution function. And in the rest of this video, we're going to talk briefly about each of them, and then we're going to talk about how to estimate them from data. The cumulative distribution function of a random variable A is the probability that the random variable is smaller or equal to any value on the real line. Okay, so we're not tracking every possible interval, we're tracking intervals that look like this. Let me draw a quick picture. So this is the real line. We're saying what's the probability that the random variable goes up to there, the probability that it goes up to there, up to there, the probability that it goes up to there. Hopefully that makes sense, okay? So it's intervals that go up to a certain point. That's the cumulative distribution function, and it always looks like this. We'll go more in detail in the video on cumulative distribution functions, on CDFs. That's what we usually call them, CDFs. But they go from 0 to 1, okay? They always go from 0 to 1, and they're always non-decreasing. If we want to compute the probability that the random variable belongs to a certain interval, we can always express it in terms of the CDF by subtracting the value of the CDF at the beginning of the interval from the value of the CDF at the end of the interval. Visually, if we want the probability that the random variable is here, we take the CDF here and we subtract its value here. Again, we'll justify all of this in the video on CDFs. A quantity that is very useful that is connected to CDFs are the quantiles of a distribution. The quantiles partition the real line in the following way. So here we have, these are the 4 quantiles, which are called quartiles. They tell us the following. They tell us in which regions of the real line the random variable has the same probability of being. What do I mean by that? That was a little bit, I think it was a bit confusing the way I said that. So like we have this random variable a, the probability that a is here is exactly 1/4 because the CDF is equal to 1/4, right? So this is the first quartile. The probability that a random variable is to the left of the first quartile is 1/4. The probability that the random variable is between the first and second quartile is also 1/4. How do I know this? Because the CDF here is 1/2, right? So the probability that the random variable is in here is 1/2 minus 1/4 equal to 1/4. And then the probability that we're between Q2 and Q3 is again 1/4 because this is equal to 0.75. And the probability that we're to the right of Q3 is again 0.25. So the quantiles, well, here the quartiles separate the real line, partition the real line into sets so that the probability that random variable belongs to each of these sets is the same. In this case, 1/4 because they are the 4 quantiles. If they were the n quantiles, it would be 1/n. Okay, that's the definition of quantile. It's very useful to very quickly describe how the distribution of a continuous random variable looks like. This is the definition. The n quantiles are n minus 1 points, such that the probability that a is in these segments that are where the boundaries are those n points is the same. Equivalently, the probability that the random variable is smaller to each of the quantiles is I/n, where I goes from 1 to n minus 1, as we saw in the picture. So they can be expressed in terms of the value of the CDF. The 4 quantiles are called quartiles, and this one is particularly important. It divides, maybe I'll show the picture again. The one in the middle divides the real line in a way that there's one, like the probability that the random variable is to the left is 1/2, and the probability that the random variable is to the right is 1/2. That point is called the median, and it corresponds to the point where the CDF is equal to 0.5. Okay, that's the median of a distribution. So how do we estimate this object from data? We have seen that if you have the CDF, you can describe the behavior of a continuous random variable. You can compute the probability that it belongs to any interval, and hence to any union of intervals, because then you just have to add up all those probabilities. But how do we estimate this quantity from data? Now we're talking about statistics as opposed to probability theory. Well, we realize that by definition, the CDF at any point A is a probability. It's a probability that the random variable is smaller or equal to A. So it's very natural to estimate that probability using an empirical probability. If you remember, the empirical probability is just the fraction of data points that are in a certain event. In this case, the event is being smaller than any particular value. Okay, so this is the empirical CDF, the empirical cumulative distribution function. It's equal to, for each, it's defined at every point A. What we do is we count the number of points that are smaller or equal to A. Remember that this is an indicator function that is 1 if a data point is smaller or equal to A, 0 otherwise. And we divide by the total number of points. Okay, so this is the fraction of points that are smaller or equal to A. I should have asked you, how do you think the empirical CDF is going to look like? Maybe, before we go into there, let's imagine that you have 3 points on the real line. So this is the real line, and we observe 3 data points. So now you can imagine how to build the empirical CDF. Let's say that this is 0. Well, now you start at 0, right? Because there are no points to the left of here. And once you are to the right of the first data point, there's 1 point there. So you jump up to 1/3, right? Then you jump up to 2/3, and then you jump up to 1. So the empirical CDF is always going to look like a staircase where you add probabilities of 1/n each time you encounter a data point. All right, I hope it's clear that the probability of being here, the empirical probability of being here is 0. The empirical probability of here is 1/3. The empirical probability of being here is 2/3. Not being here, I mean being there or smaller than that value, okay, which is what the CDF means. And that's why when we zoom in, here I'm zooming in to a CDF, it's always going to be, an empirical CDF is always going to look like a staircase. How do you estimate quantiles? Well, again, this has a very natural, like a very intuitive connection to empirical probability. We want the points for which the probability that you are that you're in each of these segments is the same, is 1/n. So you can just set the quantiles so that the empirical probability is like that. And you can do this with the CDF. So what you do is you look at the point where the empirical CDF is equal to 0.25. That means that 1/4, imagine that we're doing the 4 quantiles, right? You're doing the n quantiles, you do the same thing instead of with 4, but with n. So here, the probability that you are here is 1/4 because the empirical CDF is there. That means that 1/4 of the data points are there. This is the median, okay? Because the empirical CDF there is equal to 1/2. That means that 1/4 of the points are also here, and so on and so forth, right? So here, there's another 1/4 of the points, and here another 1/4 of the points. And we know because of the values of the empirical CDF. Okay, so basically that's how you compute the quantiles and quartiles in practice. It's actually very simple. You look at the points where, so for the median, for example, what is the point at which I have half of the data points to the left, half of the data points to the right. When we're dealing with CDFs, sometimes it's kind of frustrating that they're a very global quantity. What do I mean by that? Imagine that I tell you that I have this random variable that has this CDF. Immediately, you're probably going to start thinking about, okay, so if I sample from this random variable, where am I going to see the most samples? And looking at the CDF, it's not immediately obvious. You have to remember that the probability that the random variable is in any interval is equal to the CDF at the right of the interval minus the CDF at the left of the interval. So this essentially means if you realize that in these regions where it's flat, the probability of the random variable being there is actually 0. So in this case, if you start taking these differences in your head, you're going to realize that the samples are going to fall either here or here. And because of this slope, you're probably going to get more samples here towards the right of this interval. So essentially, and you start seeing maybe where I'm going, if you really want to understand how the continuous random variable is behaving, you're going to be almost computing a derivative in your head. Why? Because implicitly, you're trying to characterize the local behavior by looking at the density of probability. So what is the probability density? Let me show you with a picture. This is not the CDF, okay? So you shouldn't think of this as the CDF. This is, in fact, the probability density function that we're going to define in a moment. But for now, okay, I'm just going to describe to you intuitively what this object actually does. So this is the real line. And now we're going to look at the probability that a random variable is in a segment of length epsilon. Okay, this length is epsilon within the real line. What does the density tell us? The density is a number that, if you multiply it with epsilon, gives you the probability of being within that interval. This is the same as the density when you're talking about mass, right? It's usually mass divided by volume. Here we have probability divided by length because we're only considering a line. If you want to think about mass, you can think of a very thin rod, which only has mass in one direction, although that's a little bit weird. Okay, but the point is that the density tells us the probability per interval of length. And what we do is, to define densities, we take this epsilon to 0. So we say when the interval is very, 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 very small, what is the probability divided by the length of the interval? That gives us the density of points of the continuous random variable close to a certain point, A here. Okay, so we take a small interval of length epsilon around A. We say, okay, here, what is the probability divided by the length of a very, very, very small interval? When we take that length to 0, that gives us the density of probability at that point. Hopefully that made some sense. In general, we define, and we'll see the connection when we talk about a bit more in detail about probability density functions, we define the PDF or probability density function as the derivative of the cumulative distribution function of the CDF. And the reason is this argument that I said before, that at the end of the day, the density is given by changes. The probability is given by changes in the CDF, and when you take a derivative, you're implicitly dividing by the length of these intervals. Again, we'll explain in more detail in the video on PDFs. Okay, but the point is that instead of expressing or describing continuous random variables like that, we often, not usually, like the CDF can also be very useful. We often use the density, which is the derivative, which tells us where the random variable is going to be and is going to end up being. So remember my argument that you're going to see the samples here and here. You immediately see that when you look at the probability density. It tells you where more points are going to land. Because for the same length of interval, if you have more density, the probability is higher. The probability of the random variable being there is higher. Okay, great. And we compute probabilities by integrating this density. That's what you do to densities to compute mass, for example. So here it's the same. We integrate the PDF in order to find the probability that the random variable is in any interval or union of intervals. All right, so how do we estimate a density from data? There's two main ways. You can do a normalized, I was going to go into the non-parametric estimate. There's two main ways. There's the non-parametric way of doing this, and then there's the parametric way of doing this. The non-parametric estimate is based on a histogram, a normalized histogram, or on kernel density estimation. I'll explain in a moment what that is. The parametric estimates are predefined shapes for the densities that depend on a very small number of parameters that are fit using maximum likelihood. Let's start with non-parametric models. Here, these models make the assumption that the density is locally constant or at least locally smooth. Under that assumption, essentially what we do is we say, okay, for the histogram, what we do is we cut up the real line in these bins. We compute the empirical probability that the random variable is in each of those bins, and then we divide by the length of the bin to get a density, because we're assuming that within that bin, the density is constant. So we just need to divide by the length. And that's the normalized histogram, which gives us an estimate of the probability density. But there's something a little bit not really satisfying about the histogram, which is there's two things maybe that are not very satisfying. The first one is that if you think about it, actually, I was going to draw some points. I have them there. So if when we're doing a histogram, what we say is we separate the real line in bins, and then we estimate the density as being constant within those bins. But sometimes some of the points are not going to be close to the center of the bin. So their contribution to our estimate of probability density is going to, I said that in a bit of a weird way. What I was saying is that this point x3 is going to contribute to our estimate of probability density within this interval, but not here, even though this is closer to it, right? Like the points here are closer than the points here. So it seems weird that these bins have to be centered at predefined points. Another way of seeing the histogram is that we're actually adding little boxes. So maybe let me show you here. We can think of the histogram as adding little boxes, each consisting of the contribution of a single data point. We're adding little boxes that have the same shape as the bins. And each little box, if you want, has area 1 over n, so that when you add all of the little boxes, you get an area of 1, because PDFs need to have an area of 1. We'll explain that in more detail in the videos on PDFs. But those little boxes that we're adding for each of these points have to be centered at the center of the bins, instead of being centered at the data points. That's not very natural. You can actually center those little boxes, like shift them a little bit, so that they're centered at each of the data points. So here, for example, you would say, okay, I have x1 there. Let me add a little box there with area 1 over n. Then another little box centered at x2, and another little box centered at x3. If you put all of them together, you get a probability density which does not consist of rigid bins, okay? It's more like a sum of little boxes that are centered at each of the points. So if you do that, you get a kernel density estimate, which doesn't have usually the same blocky artifacts as the histogram. And in fact, you can even change your rectangles or kernels that you're using to represent each of the points to smooth them out, so that the point contributes more to the density estimate close to it and less to points that are not so close to it. Okay, and that's kernel density estimation with, for example, a Gaussian shape. And this is what we get. Okay, so a more smooth estimate of the density, which is still assuming that the density is locally smooth, right? But at least it doesn't have the artifacts that arise in the histogram or when you use kernel density estimation using these small rectangles. Again, we'll explain this in more detail in the video on nonparametric density estimation. This is how a kernel density estimate looks for a real data set, the same one where we were looking at the histogram before. So you can see that it's much smoother. An alternative to nonparametric modeling is to use parametric models. These models have a big advantage in the sense that they can be fit very robustly to very little data. We already explained this in the context of discrete parametric models. The big disadvantage that they have is that we have to make some assumptions to design the predefined shape of this distribution that depends on a small number of parameters, and those assumptions are typically wrong. Which doesn't mean that the model cannot be super useful. Nevertheless, if the assumptions are at least reasonable. We're going to talk mainly about the two most popular continuous parametric models. One is the exponential distribution, which has a decaying exponential shape starting at 0, okay, which is governed by a parameter lambda. So lambda governs essentially how fast the distribution goes to 0. As we increase lambda, it goes down quicker. And that's the parameter that we're going to fit using data. The other very popular distribution is the Gaussian distribution, which appears all over the place because it turns out that when you sum a lot of independent quantities, they tend to be approximately Gaussian. That's the central limit theorem, which we will talk about but in a while, which is super important for statistics. But that's the reason why many naturally occurring quantities, like for example the height of the population, tend to be approximately Gaussian. This is the shape that the predefined shape for a Gaussian that depends on two parameters, mu, which tells us where the Gaussian is centered, and sigma, which tells us how stretched out the Gaussian is. Let me show you some examples. This is what a Gaussian looks like, which is centered at 3, has standard deviation, which just tells us again how stretched out it is, equal to 1, sigma equal to 1. If we center at -2 instead, this is shifted to the left, and because we have increased sigma to 2, this becomes fatter. Okay, and this is another one which is centered at 0 and it's even fatter, sigma is equal to 4. When we're doing parametric model, we have to choose those parameters so that we fit the data. That's a crucial step when we're using these models in practice. And we cannot just, it's not obvious how to do it. Maybe that's my point. So here you can see the data. These are two parameters that don't really correspond to the data. This is some height data. Here again, so how do we choose the parameters so that we fit the data well? Well, we do maximum likelihood. Remember that for discrete random variables, the likelihood is basically the probability of observing the data as a function of the parameters, and then we twiddle with the parameters until that probability is as high as possible. Here, in the case of continuous random variables, we're going to maximize the probability density instead, because remember that the probability density is what tells you where the random variable ends up. So we want to maximize the probability density at the data that we observe. That's a reasonable thing to do, because it will mean that the parametric model is as consistent as possible with the observed data. So what we do is we derive the probability density at the data if the parametric model holds as a function of the parameters. Then we fix the data and we interpret that density as a function of the parameters. We call it a likelihood, and we maximize the likelihood to make the density as high as possible. Okay, we call this maximum likelihood estimation. We usually take a logarithm because as we will see, otherwise the value of the density is usually super small. Here we see what the likelihood function looks like, the log likelihood function looks like when we're choosing mu and sigma. These are contour lines and they're coming out. Okay, so you can think this like as a mountain that is coming up, and this is the peak of the mountain, and that's what we choose as the maximum likelihood estimate. So here, this would be this value of mu, and approximately that value of sigma, a little bit lower. And that gives us a very good fit to our data. Okay, that's maximum likelihood estimation for continuous parametric models. All right, so what have we learned here? We have learned the mathematical definition of continuous random variables, which is, as in the discrete case, kind of complicated and intimidating. There's this underlying sample space, this underlying probability space with its probability measure, but it turns out that we don't need it at all. We can just deal with the random variables directly in terms of the probabilities that they belong to different intervals. But how do we keep track of those probabilities? We have two main tools, the CDF, or cumulative distribution function, and the PDF, the probability density function. And then we explained also how to estimate them from data. In the case of the probability density, we considered non-parametric models, the histogram and kernel density estimation, and then we talked about parametric modeling specifically for two distributions, the exponential and Gaussian distribution. And that's all I got. Thank you very much.